Operation of addition may be viewed as both constructor and deconstructor. If we have two natural numbers and take their sum, then we get a larger natural number. So this means that now we can construct bigger numbers from smaller numbers using addition. But simultaneously, if we take a given natural number, we can break it down into a sum of smaller numbers. And in such a way, we can view operation of addition as deconstructor. The same can be done with vector spaces. Today, we are going to look at the operation of direct sums of vector spaces. And this operation can be viewed both as constructor, so we'll take two vector spaces, and by taking the direct sum, we'll obtain a larger vector space. But also as a deconstructor, we'll take a vector space and we can decompose it into a direct sum of smaller subspaces. These two operations may look differently, but in fact, these are just 2 points of view on the same construction. We begin with the definition. Let U and V be two vector spaces over a field F. Their direct sum U plus V is the set of pairs U, V, where U belongs to vector space U and V belongs to vector space V with component-wise operations. So 0 vector in this space is a pair 0, 0, where the first 0 is taken in vector space U and the second 0 is taken in vector space V. Then if we have two such pairs, U1, V1, and we add another pair, U2, V2, this is defined as U1 plus U2. We take the sum in the first component and we take the sum in the second component. And when we take constant multiple of a pair, so this is going to be CU and CV. So here C belongs to the field F. I leave for you as an exercise. So verify that all axioms of a vector space hold for the direct sum U plus V. Now let us look at examples. If we take R plus R, this is the set of pairs AB, where both A and B are real numbers. And so here we have two component vectors. And we can see that this is isomorphic to the space R2, because the operation of addition and scalar multiplication is done component-wise, just as we do it in R2. And the only difference that traditionally in R2 we write components as columns, and here we write them as rows. But nonetheless, there is a one-to-one correspondence between these two vector spaces that will preserve operations. This can be generalized if we take n copies of a field and take the direct sum. Then we get the vector space Fn, right? So this sign means isomorphic. Here we get n component expressions with component-wise addition and scalar multiplication. So vector space operations work exactly in the same way as they do in Fn. Direct sum operation allows us to put together completely heterogeneous objects. So for example, we can look at the following vector space. We can take the space of 2 by 2 matrices and take a direct sum with the space of polynomials. So here, objects of this vector space are pairs, matrix, and polynomial. So for example, if we take a pair 0, 1, 1, 0, x squared plus 3x, and add a pair 1, 2, 3, 4 with the polynomial x cubed plus 2x squared plus 4, then as a result we get a pair where we have 1, 3, 4, 4, and the polynomial is x cubed plus 3x squared plus 3x plus 4. Vector spaces U and V may be identified with subspaces in the direct sum U plus V. More precisely, we have the following lemma. Vector space U is isomorphic to the subspace U0 in the direct sum U plus V, where the isomorphism phi from U to U0 given by phi of U is a pair U, 0. I leave the proof of this for you as an exercise. And here there are two things to be proved. First of all, we need to prove that the set of pairs U0, where U runs over vector space U, forms a subspace inside U plus V. And secondly, we need to prove that the transformation phi that sends a vector U to a pair U, 0 is an isomorphism between vector space U and the subspace U, 0 in the direct sum U plus V. In the same way, we can also identify vector space V as a subspace in U plus V. Proposition. Let the set U1 through UN be a basis in vector space U, and the set V1 through VK be a basis in V. Then the following set, so we take pairs U1, 0, ... UN, 0, 0, V1, ... 0, VK is a basis in the direct sum U plus V. Here we say that if we take a basis in U and a basis in V and put them together by identifying U with a subspace in U plus V and identifying V with another subspace in U plus V, then we obtain a basis of the whole space. To prove this, we have to prove two facts: that this set spans U plus V, and this set is linearly independent in the direct sum. Now let us give names. So let's call the first set B1, the second set B2, and the third set, let's call it just B. To prove that B spans U plus V, we need to show that an arbitrary vector uv in u plus v is a linear combination of vectors from B. We know that B1 spans U. So this tells us that there exist scalars A1 through AN in F such that this vector U can be written as A1 U1 plus AN UN. Likewise, there exist scalars B1 through BK such that V is equal to B1 V1 plus BK VK. Then we take the pair UV and write it as a sum in the following way. We write it as U comma 0 plus 0 comma V. And now we substitute expressions for U and V here. So we will get A1 U1 plus AN UN comma 0 plus 0 comma B1 V1 plus BK VK. Then this can be further decomposed as A1 U1 comma 0 plus AN UN comma 0 plus B1 0 comma V1 plus BK 0 comma VK. And we proved that an arbitrary vector UV from the direct sum is a linear combination of vectors from B. So this means that B spans this direct sum vector space. Next, we need to prove linear independence. To prove linear independence, we need to take a linear combination of vectors from B equated to a zero vector and show that all coefficients in this linear combination are equal to 0. So we say, suppose we have A1 U1 0 plus AN UN 0 plus B1 0 V1 plus BK 0 VK is equal to a zero vector in the direct sum, but that's 0 comma 0. Next, we can compute the left-hand side by carrying out all operations component-wise. And then we will get that the vector in the left-hand side is A1 U1 plus AN UN, comma B1 V1 plus BK VK. And this is still equal to a pair 0, 0. When we equate two pairs, we equate their first components and second components. So from here we get that A1 U1 plus AN UN is equal to 0, but this is an equality in U. And B1 V1 plus BK VK is equal to 0. Now this is in vector space V. But the sets B1 and B2 are linearly independent. This tells us that all A coefficients are equal to 0 and all B coefficients are equal to 0. And this tells us that the set B is linearly independent. And now we proved that this set both spans the direct sum vector space and is also linearly independent. Thus, this is a basis of U plus V. As a corollary, we get that in case when U and V finite dimensional, then the dimension of the direct sum U plus V is equal to dimension of U plus the dimension of V. So here, if n is the dimension of U and k is the dimension of V, then we see that we have a basis of U plus V that contains n plus k vectors. This was the construction of an external direct sum. So this is a constructor operator. We take two vector spaces and we get a larger vector space by taking a direct sum of two vector spaces. Now we're going to look at internal direct sums. So this will be deconstructing vector space. We will take a vector space and we'll decompose it into a direct sum of its subspaces. Let us define internal direct sum. Let V be a vector space. And let U1 through UN be subspaces in V. We say that V decomposes in the direct sum U1 plus U2 plus UN if the following two conditions hold. 1. For every vector V in the space V, there exist vectors U1 in U1 dot 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 UN in UN such that V is the sum U1 plus UN. And the second condition says that this decomposition is unique. That if U1 plus UN is equal to U1 prime plus UN prime, where U1 and U1 prime belong to U1 and UN and UN prime belong to the subspace UN, then U1 must be actually equal to U1 prime and UN must be equal to UN prime. So this definition says that any vector in our vector space can be uniquely written as a sum of vectors from the subspaces. So remark. So the property 2 can be interpreted in the following way. That if we take non-zero vectors from these subspaces, so V1 from U1 and Vn from Un, then the set of these vectors is linearly independent. Indeed. So suppose we have C1 V1 plus Cn Vn is equal to 0. But the 0 vector can be written as 0 vector from U1 plus 0 vector and viewed the last vector from Un. But then, so by 2, So what we conclude is because any vector can be uniquely written as the sum, so this will tell us that C1 V1 is equal to 0 vector, and Cn Vn is also equal to a 0 vector. But all these vectors, so Vj's, are non-zero vectors, right? And then this implies that C1 and C2 and Cn must all be zero coefficients. Let us consider a few examples. So if we take the vector space R3, then we can decompose it as a direct sum of the following subspaces. Now let's take a one-dimensional subspace spanned by E1 plus a one-dimensional subspace spanned by E2 and a one-dimensional subspace spanned by E3. If we take an arbitrary vector in R3, ABC, then this vector can be expanded as A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. So this calculation shows that any vector from R3 can be decomposed in a sum of vectors from these three subspaces in a unique way. So clearly, a vector can be decomposed in this way, and each component belongs to the corresponding subspace. And if we have A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1 is equal to A prime 1, 0, 0 plus B prime 0, 1, 0 plus C prime times 0, 0, 1, then of course, by comparing components, this tells us that A is equal to A prime, B is equal to B prime, and C is equal to C prime. When we're discussing external direct sums, we saw that we can construct R3 as an external direct sum of three copies of R plus R plus R. And then the first copy of R will be identified with the subspace R times E1. The second copy of R will be identified with subspace R times E2, and the third copy of R will be identified with R E3. And here, by looking at internal direct sums, we can see that R3 breaks down into a direct sum of these three copies of R. As our next example, we consider subspaces in the vector space of 3 by 3 matrices. U plus be the subspace of strictly upper triangular matrices. So U plus consists of matrices of the form 0, A, B, 0, 0, C, 0, 0, 0, where A, B, and C are in R. Let's take D, this subspace of diagonal matrices, 3 by 3 matrices. And U minus be the subspace of strictly lower triangular matrices. Defined in the same way, only with non-zero entries below the diagonal. Then we claim that the space M33 of R decomposes as U plus D plus U minus. So what are we saying here? So we are saying that if we have an arbitrary 3 by 3 matrix, then we can decompose it as a sum of 3 matrices, a strictly upper triangular matrix. So we have 0, A12, A13, 0, 0, A23, 0, 0, 0, plus a diagonal matrix where we have A11, A22, and A33 on the diagonal, and the rest is zeros, plus a lower triangular matrix where we have A21, 0, A31, A32, and 0. And it's clear that this decomposition is unique. So there is only one way of decomposing a given matrix in the sum of a strictly upper triangular matrix, a diagonal matrix, and strictly lower triangular matrix. So this tells us that we can decompose the space of matrices in the direct sum of these 3 subspaces. And clearly, this generalizes to square matrices of arbitrary size. The next example will be the most important for us. So let T be a diagonalizable operator on a finite dimensional vector space V. Let lambda 1 through lambda k be the eigenvalues of T, and denote by V lambda 1, V lambda k, the corresponding eigenspaces. So V lambda j is the kernel of T minus lambda j times identity. Then we claim that our vector space decomposes in the direct sum V lambda 1 plus V lambda 2 plus V lambda k. Let us prove this claim. Let B1 be a basis of V lambda 1 and Bk be the basis of eigenspace V lambda k. We proved last time that if T is diagonalizable, so this is equivalent to saying that the union of this basis is a basis of V. This implies that any vector V in our vector space can be written as V equals the sum U1 plus UK, where each summand Uj belongs to the eigenspace V lambda j. This proves the first property of the direct sum. So for the second property, we note that property 2, let's recall it. So if we have U1 plus UK is equal to U1 prime plus UK prime, then this should imply that u1 is equal to u1 prime and uk is equal to uk prime. So we know that this is equivalent to the property that if u1 plus uk is equal to 0 vector, then each vector is equal to 0. And to prove equivalence of these two conditions, right, what we call it 2 prime, then all we have to do is we have to move the prime vectors to the left-hand side. And then we recall the proposition that we proved last time, that if we have u1 in v lambda 1 and uk in v lambda k, and if the sum of these vectors is equal to a 0 vector, then each of the vectors is equal to 0. So we prove this proposition using van der Monde determinant argument. And this establishes the property 2 prime, which is equivalent to the property 2, and thus this vector space V decomposes in the direct sum of eigenspaces, provided that this operator T is diagonalizable. We make the following observation, that for two subspaces, that is, when we're decomposing a vector space into a direct sum of two subspaces, the definition simplifies, and property 2 of definition of direct sum may be written as u1 intersection with u2 is a 0 vector. This follows from the fact that this property u1 plus u2 is equal to u1 prime plus u2 prime for two vectors can be equivalently written as u1 minus u1 prime is equal to u2 minus u2 prime. And then we see that the left-hand side belongs to the subspace u1 and the right-hand side belongs to the subspace u2. So this common vector must belong to the intersection. And if this intersection is equal to a 0 vector, then we conclude that the left-hand side is equal to 0 and the right-hand side is equal to 0. And this will tell us that u1 is equal to u1 prime and u2 is equal to u2 prime. But this trick only can be done with two summands. So this does not work with three subspaces. Let me give you the following exercise. Let U and W be subspaces in a finite dimensional vector space V. Then V decomposes in the direct sum of U plus W if and only if two conditions hold. One, dimension of U plus dimension of W is equal to dimension of V. And two, intersection of U with W is the 0 vector. Let's consider another example. A square matrix B is called symmetric if the transpose of B is equal to B, and a square matrix C is called skew-symmetric if the transpose of C is equal to minus C. So, for example, the matrix 1, 2, 2, 3 is symmetric, and the matrix 0, 2, minus 2, 0 is skew-symmetric. Let S plus be the subspace of symmetric matrices. In M and N of R, and S minus subspace of skew-symmetric matrices. And it's an easy exercise to show that these are indeed subspaces. We claim that this vector space of n by n matrices decomposes in the direct sum of S plus with S minus. What this says is that any square matrix can be uniquely decomposed into a sum of a symmetric matrix and a skew-symmetric matrix. Let us see how this can be done. Suppose we are able to decompose matrix A in the sum of B plus C, where B belongs to S plus, so that is symmetric, and C belongs to S minus. Now let us take the transpose of the matrix A. So the transpose of A will be equal to the transpose of B plus the transpose of C. But B is symmetric, so the transpose of B is equal to B. And C is skew-symmetric, so the transpose of C is equal to minus C. Then, if we add these two equalities, then we will get that A plus A transpose is equal to 2B. And if we subtract these two equalities, then we get that A minus A transpose is equal to 2C. This suggests how we can find this decomposition. So given the matrix A, we set B to be 1/2 of A plus A transpose. And C we set as 1/2 of A minus A transpose. Then we can see that the matrix B is symmetric because B transpose will be 1/2 of A transpose plus A, and this is equal to B. So the matrix B belongs to S plus for any matrix A. And C is a skew-symmetric matrix because C transpose is equal to 1/2 A transpose minus A, and this is equal to minus C. So this is a skew-symmetric matrix. And finally, we can easily see that B plus C is equal to A. So this tells us that we know how to decompose any matrix in the sum of a symmetric matrix and a skew-symmetric matrix, where the components are defined in this way. And from this calculation, we show that this decomposition is unique because matrices B and C are uniquely determined by matrix A. This proves that the space of square matrices may be decomposed in the direct sum of symmetric matrices and skew-symmetric matrices. Another possibility for proving this fact is to use this exercise. We could compute dimensions of the spaces of symmetric matrices and the space of skew-symmetric matrices, and then show that the sum of dimensions is equal to n squared, the dimension of the space of square matrices, and also that these two subspaces intersect at a zero vector. So that is, only a zero matrix is simultaneously symmetric and skew-symmetric. In conclusion, let us state the following proposition. Let U1 through UK be subspaces in a vector space V, with bases b1, bk, respectively. Then V decomposes in the direct sum of u1 plus uk if and only if the union b1 with b2 with bk is a basis of V. So if we join together the bases of subspaces and we obtain the basis of the whole space, then this space decomposes in the direct sum of these subspaces and vice versa. I leave the proof of this proposition for you as an exercise. And we state the corollary that if V decomposes in the direct sum of its subspaces and V is finite dimensional, then dimension of V is equal to the sum of dimension of these subspaces. Of course, the equality of these dimensions is a necessary condition for existence of this decomposition, but is not sufficient.